it in near future, as I'm telling. There's large volume production. And also you want to increase the capacity because the steel production. India is progressively want to produce more and more steel. China maybe has come to its saturation because so capacity building is coming up. And then the major route of steel production is BFBF. So it is very difficult to do away with this BFBF process in near future. And so what is required? Requires the process innovation, and that can be supplemented by low carbon, and also by this process, iron has, there is a BFBF process should be supplemented by low carbon technologies and the carbon sequestration. So blast furnace for sustainable development. Now, what we can do with the blast furnace, as I said, that it has to be almost an thermodynamic limit. So there are basically two options what I can do in the blast furnace. One option such that is emission can be reduced significantly. One option is the top gas recycling blast furnace, that is called the TGRBA. And another option is the low temperature, low emission added making into the blast furnace. I'll talk about that. First of all, that is the potential. Okay, fine. Unfortunately, this is not coming nicely. A potential technology for the blast furnace from wood cost, that is the ultra low CO2 steel making. And this is an organization in Europe, and 48 European companies and organizations are part of it. And they are developing different low carbon footprint processes. And one of the most promising one is the top gas recycling blast furnace. And this blast furnace is similar to a blast furnace where basically it replaces, there is the preheated air by pure oxygen at the bottom. And that's why it is also called the basically your oxygen blast furnace. What is the idea here is that since you are replacing the air by oxygen, basically the top gas is only CO and CO2. There is no nitrogen dilution. That is the idea. Such that, and then you can, after gas cleaning, you can scrub all the CO2 from the gas, CO2 mixture, you take out the CO2, and then the CO you can inject from the bottom of the furnace. So this is called top gas recycling. Basically, the top gas you take out, you scrub the CO2, and the CO, after preheating, you can inject again into the blast furnace. That will improve its carbon efficiency. And CO2 is basically separated by VPSA, called the vacuum pressure swing absorption. Basically, you have some carbon absorbing material, CO2 absorbing material that absorbs the CO2 under normal pressure at 1 atmosphere pressure. And then if you can, in the next cycle, if you reduce the pressure, you can take out those oxygen, those CO2, and you can liquefy and whatever you want to do it. So the separation is done by BPSA, and the top gas after scrubbing is recycled back into the furnace. And in this way, the process becomes highly carbon efficient. It has been found you can reduce the 25% carbon consumption into the blast furnace. And 50% reduction in CO2 emission if you do the sequestration. That is the whatever the CO2 you are scrubbing, if you just sequester it by liquefying it and then store it somewhere or whatever way, and then you can reduce the CO2 emission by 50%. And you can simply retrofit it to the existing blast furnace. It's not very difficult. Only your preheated air blast should be replaced by the oxygen. And the major one problem may be there into the height of the shaft. Height of the shaft, if it is maybe a limiting, it may not be very high. Although you are supplementing some amount of the nitrogen by this recycling gas, but nitrogen has also a role into the blast furnace, because it increases the heat capacity of the gas. That's basically helping supplying the heat from the gas to the solid. When nitrogen is not there, heat capacity decreases significantly. But at the same time, since you are recycling the gas, that increases the heat capacity of the gas. But this should be commensurate. If it is not, then the height of the furnace, maybe you have to look into that. Or in place of oxygen, people can think about oxygen enriched air blast. That can also improve the heat capacity of the gas if it is reduced. So another technology is the low temperature, low emission iron making technology. This is already implemented into, oh my God. Sorry, here also nothing is visible. Hello, Soumitra, can you hear me?
Yes, sir, I can hear you, sir.
So one thing, can I transfer it to just I'm in a meeting. Do after some time. Okay, okay. So should I continue with this, or I will transfer it to PDF and then give the lecture with the PDF format, or I can go ahead?
No, sir, you can continue with this, sir.
Okay, fine. So, so another is that low temperature, low emission iron making. The basic thing is that actually, that is the your FEO, that is the FECO phase diagram that is not visible. Oof. I am in a meeting part, so can I tell you after some time? Just after some time. Okay. Okay. Um, so here, actually, the FECO phase diagram is not visible, but those who have done the iron making, steel making, you are aware of it. And you know there is the FEO FE equilibrium. That is very important. If you consider the FEO equilibrium line, you have seen that for FEO FE, this indirect reduction is a highly reversible process. It is not irreversible, and around 70% of CO is required for equilibrium at 900 degrees centigrade. So at 1000 degrees centigrade or 900 degrees centigrade, around 70% CO should be kept into the equilibrium for the Woostide FE equilibrium. And if you only supply the CO above that value, that is above 70%, then only you can convert the FeO to Fe. So 1 mole of FeO will be converted to Fe when you supply CO in excess of 70% in the CO-CO2 mixture. And it increases further with increase in temperature because the nature of the curve. So at higher temperature, what you can see, that is the equilibrium CO requirement increases. And even at 900 and 900 to 1000 degrees centigrade, it is around 70%. That means you can utilize only 30% of the CO. And this is called the CO utilization. And this CO utilization decreases even at high temperature. But if you can reduce the temperature, then your CO utilization increases. That is the basically essence of this method. Basically, if you can reduce the temperature of the isothermal zone, where basically majority of the indirect reduction, FeO-Fe indirect reduction take place, if you can reduce the isothermal zone temperature from 1000 degrees centigrade, so 800 or 700 degrees centigrade, then you can increase the CO utilization. As you increase the CO utilization, obviously your carbon utilization, carbon efficiency of the blast furnace increases. That is the idea. And what you can see in the upper is the basically operating line. Operating line, you know, basically comes from the material balance, material and heat balance. And this operating line, slope of this operating line give you the basically the carbon rate into the blast furnace. It has two fixed points. One is called the thermal pinch point that basically come from the heat balance. That is the fixed point for a particular heat demand or for a particular blast furnace operating with certain material. There's thermal pinch point is a fixed, and this Woostide equilibrium point is also fixed because you cannot operate below with a below that is the below lower level of the CO, because you have to achieve the equilibrium point, then only the Woostide reduction will take place. And final reduction is the Woostide to iron. So you cannot cross the Woostide line. Okay. So this is two line basically fix up the what is the minimum carbon rate into the blast furnace. And if you can reduce the isothermal zone temperature, what you can find that you can Woostide this point, Woostide equilibrium point, can be shifted on the right hand side right here. As a result, the slope of the operating line will decrease, and that basically will reduce the carbon rate. So you can reduce the carbon rate further. Okay, so if you can reduce the temperature of the isothermal zone, but it is not a very easy task to reduce the isothermal zone, because in the isothermal zone, the major reaction takes place is the carbon gasification reaction, that is the in situ generation of the CO. And for that, since it is a highly endothermic reaction, so uh, it is very difficult to carry out the carbon gasification reaction to the full extent below the 900 degrees centigrade. Okay, so that is the limit. Okay, so but you can reduce the isothermal zone temperature and maintain the carbon gasification reaction somehow if you can improve the reactivity of the coke. If the reactivity of the coke increases, then you can possibly carry out the carbon gasification reaction to its fullest extent, even below the 900 degrees centigrade temperature. So by reducing the activation energy. And also it has been found that iron ore composite pellets or briquettes also can reduce the isothermal zone temperature, and it has been found. And also you can use some external reform gas into the shaft furnace that also can uh, help in reducing the isothermal zone temperature. Basically, if you want to reduce the FUF reduction at comparatively lower temperature, these are the possibilities. Okay, so Nippon Steel already has done it, and they have demonstrated that they can reduce the carbon reduction by 170 kg per ton of hot metal. So now I'll just talk about some of the broad classification of methods of decarbonization in steel industry. What are the major classification? So first is that the technologies that retain the fossil carbon as the key reduction agent into the iron making, but want to mitigate the CO2 emission that arises, just like BFBF process. Okay, it is basically you are using the fossil fuel, you have no other way of using it, but you want to mitigate the CO2 emission that arises out of it. So there are several methods are there. You can, whatever the CO2 is coming out, you can sequester to some extent, or you can convert the CO2 to a carbon neutral fuel like methanol, people are doing also. Okay, or you can use the CO2 for beverage production like the cold drinks and etc. And then finally, you can take the CO2, you can liquefy it, and then underground storage you can send it. So that is the one method, that is the technologies that want to retain the fossil carbon as the key reduction agent. And because in BFBF you have no other route also, only you can mitigate the CO2 emission that arises. Second is the technologies that seeks to avoid the generation of the CO2 by fuel switching. What is that? For example, if you consider the direct reduction of iron. Previously, we were doing with the coal, right? Coal was the fuel. Now, in the gas-based reduction, what we did, basically we have changed the fuel from coal to the natural gas. And obviously, the natural gas is a very low carbon intensive fuel, because for 4 hydrogen, it contains 1 carbon, right? It gives more hydrogen than that of the carbon, circle CO2. So there, so in the DR reduction process, we have do the fuel switching already by natural gas, and as a result, the carbon emission has come down to a significant extent. This is just an example. So you can think about technologies. These are the technology that can avoid the CO2 generation by fuel switching. Then third is the technology that seeks to incorporate renewable electricity as a partial replacement of fuel based on smelting. That is the partial replacement of the fuel-based melting energy. So if you can use the renewable electricity, and best example is to the electric arc furnace. In electric arc furnace, the electricity that we are using is based on the fossil fuel. Basically, we burn the carbon, generate the steam, and then we produce the electricity. So it is completely carbon-based electricity. If we can replace by renewable electricity, then it will be totally carbon-free. So that is the thing, technology that seeks to incorporate the renewable electricity as partial replacement of fuel-based melting energy. And finally, the circular economy, you can, based on the scrap usage into the electric arc furnace, if you can do that, that is the best option. And then the scraps recycling into the electric arc furnace can be totally carbon-free if you use the renewable electricity also. So first of all, one by one, if we take out, then if you consider the mitigation, there's the emission mitigation using the sequestration. One effective way to mitigate the emission for the coal-based technology is the carbon capture and its utilization and the storage. Okay, CO2 may be used in the beverage industry, as I say, or as carbon neutral fuel like methanol. You can convert the CO2, but here also you require the hydrogen. The question is how you'll get the hydrogen. So anyway, so if you can do that, then you can neutral, that is, you can make the carbon neutral methanol, or it may be stored in the enhanced oil recovery. You know, in the underground oil recovery, if you inject the carbon dioxide, you can enhance the recovery of the oil. Okay, basically in that case, you dissolve the CO2 into the oil, and then it basically enhances the carbon. That is the oil recovery. So that is the one way people do it to uh, remove the CO2 from the system. Or you have geostorage, mineral sequestration, ocean storage, all things are there. And maximum realistic CO2 avoidance by CCS is approximately 65%. It is from the paper of the Virat et al. And because when you want to sequester the CO2 also, you have some other equipments involved in it, and it has also its own CO2 emission. So you want to reduce the emission of one process, at the same time you're producing some amount of CO2 from the from the process. Okay, so you have some realistic CO2 avoidance that is around 65%. You cannot do 100% reduction because the equipment that will be used for CO2 capture and all these things, that also involves a lot of carbon. That is the energy, and that energy source, if it is carbon, then it also emits energy. So CO2 avoidance cost is quite highly today. It is around $60 to $90 per ton of CO2. So it is not easy to take up the CO2 sequestration. And this implementation requires some kind of government intervention in terms of the carbon tax of the allowance. Government can give some allowance. That is, if you can basically remove 1 ton of CO2 per ton of crude steel, I will give you this much of allowance, like that. Or if they can put the carbon tax, because if you emit this much of carbon dioxide into the atmosphere, you have to give some certain amount of tax. Then that way, government can enforce this is actually the CO2 avoidance by sequestration. Bioenergy and carbon capture and storage basically has potential to reduce the BAPM reduction much below the 0.6, much below, and it can easily attain 0.6 ton of CO2 per ton of crude steel to achieve the 2DS. Okay, so it is possible if you use the bioenergy, that is the biomass, and also the carbon capture, storage, and all these things. Sources of basically the sources of concentrated CO2 for sequestration may be the top gas recycling blast furnace, because here the CO2 is also almost pure CO2. And another smelting reduction process that is emerging, that is called the Hisarna process. Here also the CO2 is completely, that is the CO2 that comes out is on the 100% pure CO2. So there the capture and sequestration is much easier. But other CO2 source from the steel plant, very lean source, they are very lean source, and there the cost involved of sequestration is also much higher. Emission mitigation using the biomass, the areas of biomass application in the steel plant, you know, already the biomass in the research level it is there, and also some implementation. It has come very slowly, but in the research level it is there. So biomass has been applied for sintering solid fuel. That is, in the during sintering we use the basically the coke breach, so we can replace the coke breach by the biochar, and then we can produce the sinter. And it has been found that there is a limitation because the sinter quality deteriorates beyond certain replacement of the coke breach by the biochar. Okay, so similarly we can use it in the coke making. We can basically blend, during the blending of the different coals, we can use some amount of the biomass, and then we can reduce the coke, and it is also sometimes called the biocoke. And most successful is the tuer fuel injection as the charcoal. We can inject the charcoal through the blast furnace tuer, and it has been theoretically shown that is the 100% replacement of the pulverized coal by the charcoal is possible, considering the heat and mass transfer into the process. And also some plants also demonstrated the charcoal injection into the blast furnace. Then iron ore carbon composite briquettes. we can use into the rotary earth furnace. In the rotary earth furnace, there is a scope of using the biomass as a carbonaceous source during the briquetting, because those briquettes do not require sufficient strain. So those briquettes can easily be charged into the rotary earth furnace and can be converted to the sponge iron for successive melting, either into the blast furnace or in the electrical furnace. And the biomass also can be used as a decarburizer into the steel making. It can be charged into the as a decarburizer. That is, if you increase the carbon into the process. The Mosa et al. Estimated that 40% reduction in emission by biomass is possible, and that we can reduce the carbon emission from 2 to 1.3 ton of crude steel. But one thing is that biomass need to be upgraded, because biomass contains a lot of volatiles and the carbon is not concentrated. So you have to concentrate the carbon, and for that you require some pre-treatment, and that is called the pyrolysis or the torrefaction, such that you can concentrate the carbon, okay, and then you can improve the quality of the biomass for subsequent use. And but it involves the cost. Now the pyrolysis process is take out little higher temperature, and in that process also the carbon yield also, that is the yield of the process, is less. Energy yield, mass yield, both are less. And in case of the torrefaction, which is carried out at comparatively lower temperature for carbon concentration, there the mass yield and the energy yield is little better. That's why people are going for the torrefied biomass nowadays. And but it should be into the still in the research level how much we can do that. The cost of the, that's why the cost of the charcoal increases. Cost of the charcoal does not favorably compare with that of the coal. Coal is much cheaper compared to the charcoal, at least 3 times cheaper than that of the charcoal. That is the major problem, and that's why again the carbon tax and the allowance can facilitate this implementation. Norgate showed with an Australian perspective, he has estimated the price of the charcoal at 386 USD dollar per ton. A carbon tax should be applied, that is 95 to 150 USD per ton of CO2. So if you can apply a carbon tax of 95 to 150 USD per ton of CO2, then you can purchase a charcoal at a cost of 386 USD per ton without losing anything. Okay, so this is from the Australian perspective. Similarly, so Pavarji also has given, that is the what should be the carbon allowance with respect to the Finland perspective, and they said the allowance of 50 euro per ton of crude steel should be considered. And finally come the hydrogen steel making, and in the future actually we have to go for the hydrogen steel making. Also, if you have to go for the net zero, there is a hydrogen steel making and the scrap refining, there is a recycling. That will be the only two methods by which we can achieve the net zero. But hydrogen, there is a hydrogen production that is the most important concern today. Hydrogen can be stored from the fossil fuel or for the renewable source also. Fossil fuel means basically you can still refine the natural gas, and that is the majority of the hydrogen that is produced today is by the steam refining of natural gas. But obviously steam refining produces also carbon dioxide, because methane contains at least 1 carbon per 4 hydrogen atom, right? 1 carbon is there. That's why 1 million, there's a 90 million ton of hydrogen that is produced today by steam refining that emits around 900 million ton of CO2. And renewable hydrogen, that is basically produced by water splitting using the solar energy, okay, and that is only 1 million ton per annum today. Okay, so majority of the CO2 produced today is from the steam reforming, which emits significant amount of CO2 into the atmosphere. Okay, so entire steel production of 2,500 million ton by 2050 using only renewable hydrogen, if you want to do that, then the electrolyzer capacity should be 1,000 gigawatt. It's a huge amount. Today we know the maximum capacity of an electrolyzer may be 500 megawatt, and that can produce only 1 million ton of hydrogen. Okay, so So that is the capacity limitation is also there. But anyway, over the years it will develop. And the cost of hydrogen is also today is very high. Renewable hydrogen cost around $5 per ton compared to steam reforming of methane, that is $2.5, approximately twice. So capacity as well as the cost, both are the different for the hydrogen steel making. Okay, but we can always consider the fuel mixing is an opportunity. That is we can consider the methane and hydrogen. Okay. So SSSB today we have the hybrid technology, that is the SSAB and LKAB in Sweden. SSAB is basically a steel making company, LKAB is a mining company, and the Batten Wall is also an energy company. They have combined and introduced this hybrid technology, where basically you can produce the steel from renewable hydrogen. Okay, they have demonstrated, but they have demonstrated with a small scale, and also they have a huge hydrogen storage underground. So to continue produce it, even in the when there is sunlight is not there, you can supply the hydrogen from there. Now I will talk about. I have just 10 minutes time. I will not go about. I will talk about some existing carbon-based technologies. Let us see the rotary kiln process. Oh my God. Okay. It is the most popular and the most rugged steel making unit. That is the iron making unit is the rotary kiln process. But you know the rotary kiln is very popularly used in India, and the majority of the direct reduced iron that is produced in India today, maybe 50 million ton, out of which 80% is produced by this rotary kiln method. Okay, because it is very popular and very rugged system, and you can utilize it. So what are the coal basically here used as a reductant as well as heat source. So here basically you have some coal stove for fuel switching. That is the coal. If you can replace by natural gas or hydrogen, we have to think about it. So that is the one thing. And the waste gas that is coming out, that has to be completely dedusted, and then it will be used for the power generation. So these are the things we have to do such that we can reduce the carbon footprint of the process significantly. Okay, so that is the thing that is in the rotary kiln. We have looked for the fuel switching option. Then the RHF based process are there, and as I know that the RHF based process is a highly sustainable process. Although in India we do not have any units, but it has several units in China and otherwise. And it is used for any kind of solid waste, iron bearing solid waste that is generated during the steel making. You basically what you do, you take the that is the iron bearing solid waste and mix up with some kind of carbonaceous metal, make the briquette and prelate, and naturally endure it and put it into the furnace, and then you can get the sponge iron. So that way it is always sustainable because it is utilizing the waste. Again, if we see the data, you can say it is a dual fuel furnace, the rotary earth furnace, because here the reductant is mixed with the basically input raw material. Okay, that is the reductant. It is totally independent from the heating source. That is the heat is supplied by the natural gas. Okay, so here basically the coal that is used is around 80% with 80% carbon. There are 400 kg of coal is used along with the iron ore mix. Okay, and natural gas is used 80 normal meter cube for heating purpose. Total input energy is around 10 gigajoule, and the CO2 emission is 1.2 ton per ton of DRI because the carbon input is significantly lower. Okay, and it can be 1.5 ton per ton of iron produced, that is considering 80% iron in the DRI, and it will be around 2.1 ton of CO2 per ton of crude steel, considering the melting energy and associated CO2 emission. So here, as I said, there is a scope of biochar into the composite brick or a composite briquette or the pellet, because it will completely replace the fossil carbon by a carbon neutral biochar. You can replace it. And then in that case, and if you use the natural gas, the heat production, your CO2 emission can be significantly reduced to 0.1 CO2 per ton of crude steel. Then the scrap DRI EF steel making. The scrap-based DF steel making with minimum emission, that is around, as I say, 600 kilowatt per ton of crude steel, or which correspond to around 0.48 ton of CO2 per ton of crude steel, considering that is the 1 kilowatt watt is equal to 0.8 ton or 0.8 kg of carbon. That is the Indian grid. However, the energy intensity with respect to the primary energy could be 10 gigajoule per ton of crude steel, that I say. Today, 30% of the steel produced by the scrap EAF route. It is expected to increase, but not to a great extent in near future in India. Per capita steel consumption and the end of life scrap generation need to increase significantly. So, especially in India, we have very scrap limitation. We do not have much scrap, and that's why, because we have end of life scrap is very less, which is the in-house generated scrap that is used already into the steel plant, but end of life scrap is very less. So, and it will increase with increase into the per capita consumption. Today, per capita consumption in India may be 100 kg, is quite less compared to world average of 300 kg per person. But we have a huge domestic market, and we can grow, and then we can generate the scrap also. So gas-based DRI melted into the EAF. That is the thing. That is this is the gas-based DRI that you know the carbon footprint is minimum 1 ton of CO2 per ton of crude steel. DRI produced by the reformed methane here, and the DRI produced by, this is very important. That is the coal gasification and the syngas you can use for the DRI production, and then also you can reduce the carbon footprint significantly, provided you sequester the CO2 that is generated during the coal gasification. If you leave this CO2 into the atmosphere, then it is of no use. But if you can sequester that CO2, obviously, the coal gasification coupled with DRI can give a very low carbon process. It can be only 1.3 ton of CO2 per ton of crude steel. And in India, where we have a lot of carbon resources, coal resources, so we must think about for the carbon gasification, but also we have to look into the sequestration aspect. Hydrogen DRI melted in EAF using renewable hydrogen electricity. It is basically the net zero option, and hybrid is an example, but its capacity nowadays is very low. If we can improve the capacity, obviously, what I think is that this process in Europe will be very popular very soon, because if you consider the grid carbon emission into the Europe, it is very, very less compared to us. Our grid emission is around 0.8 kg per kilowatt hour, where in Europe it may be less than 0.1. So that is the thing, because in their grid there are a lot of renewable energy that are being added, because wind energy and then hydel energy, solar energy, everything is adding in their grid, because they have achieved it significantly as far as the energy production is concerned. They are much more renewable compared to us, and then we are also going that direction, especially into the energy sector. We are trying to reduce the carbon footprint. And the EAF, RHAF, this process, as I said, it is a very sustainable process from that point of view, because you can use any kind of solid waste that is generated into iron-bearing solid waste that is generated into the steel plant. And also, there are a lot of scope to reduce the carbon footprint in the RHAF process. We have done basically a lot of research work in this area, CFD calculation, energy analysis, as well as laboratory scale experiment, how we can reduce the carbon footprint into this process. But I do not have much time to talk about those things. But next time, if I have time, I will discuss about those. Then another process is the smelting reduction process, Codex process. If you see, the Codex also have a very high coal rate, 1060 kg, and the CO2 emission can be 3 ton, and total energy 28 gigajoule, SEC can be 16 gigajoule, off gas energy 12 gigajoule. And if you do the power generation at 130 megawatt and the rate of 35% efficiency from the primary energy source, that is coal, and if you produce at 1000 tons per hour, and then the carbon credit from the power generation can be obtained 1 ton of CO2 per ton of crude steel. That is basically from calculation, you can simply calculate, and then the net emission becomes 2 ton per ton of hot metal. So, and if the export gas can be used for the DRI production, then the specific CO2 emission can be reduced more than that. So concluding remarks, so we can say for a large-scale coal-based iron and steel sector where capacity growth needs to be foreseen, process improvements of integrated plant routes and new technology addition is the primary requirement. In short term, what you can say, limited emission reduction for BF route up to 2 ton of CO2 per ton of steel, because we know today average BF emission is 2.2 ton of CO2 per ton of steel, but we can limit this BF emission, that is to from 2.2 to 2.0 ton of CO2 per ton of steel. And although use of bioenergy and the limited sequestration can reduce this value to 1.8 ton of CO2 per ton of crude steel. Okay, so by process involved, that is the improvement, because there is also some scope for the energy optimization in the blast furnace in several places. So by that, basically we can reduce the CO2 emission from 2.2 to 2. And also if you can use some bioenergy like the biomass, that you can use definitely. And if you can do some limited sequestration, then the CO2 emission can be reduced to 1.8 ton of CO2 per ton of crude steel. That is the short-term goal. Capacity enhancement for the DRI routes needs to use a large fraction of the low carbon inputs such as natural gas along with the limited green electrolytic hydrogen as available. Right, that is the thing. If we want to make a capacity enhancement in the DRI route, then we have to think for this. That is the low carbon input fuels like natural gas. We have to use it, and also we can supplement it by the limited green electrolytic hydrogen wherever is possible or available. DRI production using coal gasification with sequestration also needs to be integrated. In the longer terms, the input of green hydrogen needs to be substantially stepped up along with the implementation of newer smelting routes such as Hisarna, top gas recycling, both of which would require additional sequestration capacity to be put up. That has to be mentioned. And large circular steel production with adequate scrap may alter these integrated preferences. So when we can reach the circular economy, then obviously all these preferences can be totally changed. Okay, so with this I would like to conclude it, because I thought that our research I'll talk about it, but I do not have time. So thank you very much.
So thank you very much, sir. So now I will unmute individually the students. Whoever have question, please raise your hand. Then I can unmute you, and then you can ask question to professor. So anyone have any question? Okay, sir. So no one have any questions. So we can conclude, sir. Okay. So thank you, sir. Thank you very much for your time. And sorry for the inconvenience at the beginning. Sorry for the delay also. So and thank you for your valuable time, sir. Thank you very much, sir.
Okay, thank you, Soumitra. We are done. I am leaving.
Okay, sir. I will in touch, sir.
Okay, how to leave it? I am not going to leave it.